Hello everyone and welcome to the presentation. My name is Autarkic from XRG Simulation and I will be describing our recent work where we assess different types of hydrogen storages used as a long-term energy buffers for a local household, and that in terms of economics and energy autarky. So let me introduce you to the topic. If we have a look at the renewable energy law, for example in Germany, it aims for 80% of electrical energy being supplied from renewable energy sources. Decentralized energy systems can be an option, and this way to avoid building up extra transmission lines in order to transport energy from one part of the country to the other. Such alternative can be in the form of hydrogen battery comprising of electrolyzer, fuel cell together with hydrogen storage, and an energy management. Such a modular design of hydrogen battery was applied to passive houses residential area in Germany and serve as the key reference point. First, we had a look at different hydrogen technologies and found out that basically just two are applicable for small-scale residential areas, and these are pressurized storage and liquid organic carrier storage. Each of the technologies has its pros and cons, which are summarized here. Other approaches of storing the hydrogen are currently either too expensive, too complex, high energy demanding, or simply technically immature. Then we had to preliminary size the components of the system, and how we did that? Well, we simply set up capacities and peak power values of components by reasonable engineering guesses with respect to availability on market. The electrical demand for household appliances plus electrical demand for heat supply is extracted from the real data processing 9 individual houses. What was our workflow towards simulations? Firstly, we simulated the process model in TransiEnt software with all the technologies. That means photovoltaics, batteries, electrolyzers, fuel cells, and H2 storages. And linear optimization, which had overlook for the whole year of all input data, such as weather forecast, electricity consumption, etc., reshuffled the photovoltaic production between the battery and the storage. But of course, this is not reproducible in real conditions and extremely dependent on highly specific input data. However, it gave us ideal case, the upper boundary for the Modelica model, which considers the real behavior with all the physicalities. And by simulating it in Modelica, we could check the feasibility of the design and check how realistic is this ideal case. For the linear optimization, the pressurized hydrogen storages were analyzed in 3 different variants that were 200, 300 and 400 capacity of hydrogen. It is clearly visible that the storage capacity of 400 shows the best performance regarding autarky. On the graph, we can see mass of hydrogen for different storage capacities over 1 year starting from March. The maximum capacity is reached in late autumn, but then the photovoltaic supply gap and the high energy demand of the heat pumps in winter months lead to rapid decline of the mass of hydrogen. As a consequence, high amounts of hydrogens have to be stored, and it is crucial to maximize the stored hydrogen mass in summer. For this, decisions have to be made, whether to store extra energy in batteries for short term or store it in hydrogen batteries for long term. To achieve this, real operation has to be simulated, and we did that in Modelica. We used TransiEnt Modelica Library since it already includes comprehensive collection of models to describe and analyze integrated energy systems with high share of renewable energies according to environmental and economic aspects. All supplement models developed within this project have been put together in Extra Hydrogen Modelica Library, and it consists of models of control logic, electrolyzer, fuel cells, storages, compressor, separator, cost model, etc. Basically all that needed to be included to create final model, which can be seen here and will be described in presentation further on. The overall model of the system has been developed at different levels of complexity. Firstly, a simple model with no logic has been created in Modelica entirely from TransiEnt library components. It uses all boundary conditions given from the linear optimization results, such as electricity demand of households, electricity flow to and from batteries, electricity production from photovoltaics, and electricity production from fuel cells, and electricity demand by electrolyzers. Basically, only the electricity flow from and to the grid is let to be calculated. The boundary conditions are specified by hourly based timetables, and the model is connected to LAMP grid model to mimic European grid. The figure here shows calculated electricity flow for 1 year operation by linear optimization and Modelica model with no control logic. Electricity from the grid is in red and electricity sent to the grid is in blue. And as we can see, they match quite well. In the final system model, fixed boundary conditions for usage of electrolyzer, fuel cells and batteries were replaced by physical models and corresponding control logic. The fixed boundaries were for photovoltaic production and electricity demand of households. The system model plus the control logic were kept the same for all storage technologies. Next step was the development of simple logic model for distribution of energy flows between grid, batteries, electrolyzers and fuel cells. And the logic is as follows. First, we compare the consumption and production of electricity. And in case we have excess power, it is sent to battery if they are not full. And if they are full, it is sent to electrolyzer to produce hydrogen. But if the hydrogen storage is also full, then it is sent to outside grid. On the other hand, in case of demand power, it is taken from the battery if they are not empty. And if they are empty, it is taken from the fuel cells if the storage is not empty. And in case of empty storage, the power is taken from the outside grid. The figure reveals the limitation of the simple logic. Maximum mass of hydrogen storage that is possible to reach with this simple logic is only 230 kilograms, while the results from the linear optimization show 400 kilograms. Clearly, this is caused by the fairly immature control logic applied for initial implementation. So we improved the simple logic by adding 2 extra features to maximize the hydrogen production. Firstly, in case of excess power, the logic is enabled to simultaneously run electrolyzer and charge batteries. And second improvement we did was that in case of power demand, the battery usage is optimized such that if battery has capacity, it shall distribute its power between household consumption and electrolyzer. This is controlled according to PID controller. The PID controls the capacity level of the battery based on the forecast model. And the forecast model looks 24 hours ahead for predicted power consumption of households and assumed power production from photovoltaics. The integrated sum for upcoming 24 hours for these 2 powers gives the required needed capacities for the batteries, which is then scaled and used in the PID controller. And finally, with this improved logic, a maximum of 400 kilograms of hydrogen can be reached, which is in agreement with the linear optimization analysis. However, what the figure additionally shows is that when we further implemented physical constraints to mimic realistic behavior of the system, such as standby losses, minimum powers, time-dependent efficiencies of fuel cells and electrolyzers, hydrogen mass reduces dramatically by 60 kg for pressurized storage and by 100 kg for LOHC due to the worse efficiency of the process. We can further add, for example, forecast errors to the model and look at the influence. Or we can vary the geographical location. And that's what we did. So the reference location was central Germany, and we wanted to see how it looks, for example, in Copenhagen and Marseille. So we could see that this is all possible to investigate with minimum extra modeling effort to further evaluate the results. One of the key performance indicators for effectiveness of hydrogen storage is the level of autarky, indicating how self-efficient system is. You can see the comparison of different variants of hydrogen storages with regard to level of autarky. The variant with 400 kg pressurized storage has the highest autarky level. Here the level of autarky for the realistic behavior is 91 or 93%. That would mean that the households would take from the electric grid approximately 3.4 megawatt-hour per year, out of the total consumed electric power 37.5, and the system would be totally independent except for 25 days of the whole year. The worst combination regarding level of autarky is the LOHC variant due to the poor efficiency of the LOHC process. This variant is just 4% higher compared to the system with batteries only, so the system without any hydrogen storage. We can further see that the level of autarky reaches 97% for the Marseille location. So basically adding some additional renewable source like a wind turbine, it would be realistic to achieve totally independent system in European cities. Together with the technical analysis, an economical analysis for 30 years of operation was performed as well. We can see the final comparison of different variants of hydrogen storages. The cheapest variant is the pressurized 200 kilograms with bottles. However, the 400 kilogram storage using bottles is just 150,000 euro more expensive and offers much more flexibility and much higher level of autarky. The 400 kilograms pressurized storage using tanks is the most expensive variant, even more expensive than the LOHC. And for the conclusions, unfortunately, from today's perspective, applying H2 storage doesn't pay off economically. It would need technical improvements, and also it would need to change political conditions. For example, increasing electricity price over time, governmental subsidiary programs, or improved efficiency of fuel cells and electrolyzers, and lower component prices as well. As for today, pressurized and LOHC storages are the favorite choices in terms of technical readiness, safety, and economy. The developed system model, including control logic, is quite universal. It can be extended by other energy producers, such as wind turbines, while keeping the control logic untouched, so that the energy system can be customized to specific needs. Our work demonstrates the necessity of dynamic simulations in the design process of the hydrogen batteries, and we could see that the effects of control decisions and physicalities have substantial impact on the level of autarky. Thank you for your attention, and I'm looking for the discussion.